Okay, students, back again. I just checked what I'd recorded earlier, and we'll see if I can get it edited and get it up, but it looks like it's chopped it up into different pieces, so maybe an interesting night trying to edit this and put it together. I may have to do this in smaller chunks. But let's take a look at 1110. So basically this is saying, okay, let's start with a function. Let's go the other way. Rather than start with a power series and see what function it is, let's start with a function and see if we can come up with a power series for it. Okay. So I'm going to take an arbitrary function f of x. Let's assume it has a power series. Sum n equals 0 to infinity cn x minus a to the n. Right? So a function that has such a power series, if a happens to be 0, so we're centered at 0, we call this series a Maclaurin series for the function. If a is other than 0, then it's a Taylor series. So a Maclaurin series is just a special case of a Taylor series centered at 0. Okay? We're going to do it arbitrarily and see what do we have to have true for the coefficients. Okay? So let's write out some terms. My first term is C0. My next, when n is 1, I get C1 x minus a. When n is 2, I get C2 x minus a squared. I'm going to write out a couple of these. Actually, let me move this whole thing over. That was poor planning on my part. Give myself more space over there. So f of x is the sum, n equals 0 to infinity cn x minus a to the n, which is c0 plus c1 x minus a plus c2 x minus a squared plus c3 x minus a cubed. This is looking a little ridiculous, but I'm going to want these terms, as you'll see in a minute. X minus a to the fourth plus c5 x minus a to the fifth, etc. Okay. So how can I get my hands on the coefficients? Well, an easy coefficient to grab would be C0. If I could zero out all of these terms, the way I could zero out all of these terms is plug in x equal a. So if I plug in x equal a, I see that f at a is C0 plus a bunch of zeros. So my C0 coefficient is f at a. Now I'd like to get my hands on C1. So how could I get rid of the x minus a? Well, one thing I could do is try to divide through by it, but then I'm going to have that as a term here, and who knows what we always have to be careful about dividing by 0, right? So another way to get rid of this term would be to differentiate it. So what happens if I differentiate this? Let's see, f prime of x, C0 goes away, I get C1 times x minus a, bring down the power 1, x minus a to the 0, but x minus a to the 0 is just 1. That's how I get to C1 by itself. Then I get 2C2 x minus a to the first plus 3C3 x minus a squared, right? Plus 4C4 x minus a to the third. You see why one of these extra terms, plus 5C5 x minus a to the fourth, etc. If I plug in a to this mess, it'll kill all these terms and I'll just get C1. So C1 is f prime at a. Which point you might think you see a pattern. Well, C2 would be the second derivative of f of a, C3 would be the third derivative. Doesn't quite work like that. Let's do another derivative. Kills that. This becomes just 1, so I get 2C2 plus 3 times 2. I'm not going to multiply that out. 3 times 2, C3, x minus a to the first, plus 4 times 3, x minus a squared, or I've lost the C4, 4 times 3 times C4, x minus a squared, plus 5 times 4, x minus a cubed, etc. Plug in x equal a, will kill all of these terms, will give me 2C2. So 2C2 is f double prime at a, so C2 is f double prime at a over 2. I have to divide through by the 2. Do it one more time. Differentiate again. The third derivative at x, let's put a 3 up there rather than 3 primes. This term goes away. I get 3 times 2 times c3, and that derivative is 1. Then I get plus 4 times 3 times 2c4, x minus a to the first. All right, bring down the power, decrease the power by 1. Plus 5 times 4 times 3, x minus a squared, plus etc. Plug in x equal a to this, it kills all those terms. I get 3 times 2 c3 is f, the third derivative at a. So c3 is the third derivative of f at a over 3 times 2. Okay. For the 3 times 2 times 1, I can include a 1 in there. So I think you can see C4 will be the fourth derivative of f at a over 4 factorial. Okay. All right, I'll bring down this, differentiate again. I'll just get 4 times 3 times 2 C4. X equal a will kill the rest, okay, etc. In fact, Cn will be the nth derivative at a over n factorial. So this will work if I have a function that has infinitely many derivatives. If I can differentiate it in infinitely many times. Okay. My favorite function to differentiate infinitely many times is the exponential function. Right? So actually I'm going to look at for a Maclaurin series. We'll do one centered at 0 for the exponential function. So the game is, what are the coefficients? Let's come up with the coefficients, right? So let's find the Maclaurin series for f of x equal to e to the x. Okay. So since it's a Maclaurin series, our center A is going to be 0. So I'm going to write, I want to write this as the sum n equals 0 to infinity Cn x to the n. And I want to figure out what are my Cn's, x minus 0 to the n. Okay. So let's see. I've got no, f of x is e to the x. My a is 0, so f at 0, another reason for picking this point is e to the 0 is nicely 1. So that tells me C0 is 1. Okay. Let's differentiate. What's the derivative of e to the x? It's e to the x. Okay. What's the derivative evaluated at 0? It's e to the 0, which again is 1. Okay. So C1 will be 1 over 1. 1 factorial, which is also 1. Okay. Second derivative, that's e to the x again. So the second derivative at 0 is e to the 0 is 1. So C2 will be that 1 over 2 factorial. Okay. What's the nth derivative? So the nth derivative is again e to the x. It's always e to the x. So the nth derivative at 0 is e to the 0 is 1. So that's my numerator. My Cn then is going to be 1 over n factorial. There are my general coefficients. Okay. So a Maclaurin series for f of x equal e to the x. That's my coefficient. So e to the x equals the sum n equals 0 to infinity x to the n over n factorial. Okay. This is the guy we looked at previous lecture when we were first looking at power series. This is the guy that had an infinite interval of convergence, right? Or infinite radius of convergence. The interval of convergence was all x. Okay. Write out some terms. This is 1 plus x squared over 2 factorial plus x cubed over plus x cubed over 3 factorial, x to the 4th over 4 factorial, etc. Okay. We now know what that series converges to. It wasn't a geometric series, so we couldn't figure that out, but now we know it's e to the x. In fact, if I add up all of the factorials, so this is one you may have tested back during the ratio test. If you had just the series sum n equals 0 to infinity of 1 over n factorial, you would have tested it to see that it converged absolutely. Of course, it's a positive term series, but you wouldn't have known what it converges to. But now we know it converges to e to the x, where x is 1. Okay. So this actually adds up to e to the first, or just e. Okay. So if you ever need to approximate the number e, you can add up 1 over the factorials. The farther you go, the smaller this number gets. You can get as close to you like as e to e. Okay. Right. Slick. Another one to look at that's easy to differentiate. And I think I could do a Taylor series for this, but I'll stick to Maclaurin series because it's good to know these Maclaurin series. Actually, let me pause here, stop the video, and then I'll start again with the next example.